This is a new science that I cannot even begin to tell you how profoundly this algorithmic problem solving has affected not only our technology, our science, our engineering, but also our culture. I mean, look around. What aspect of your life is not affected by computer technology today?
I think there's just an enormous number of challenges, so I've never even thought about running out of them.
I also think that some of the most intriguing questions confronting humankind are computer science questions. How does the brain work? What makes us human? Are we biological computers that can be simulated by mechanical computers? Does this mean that we could imbue computers with human-like attributes, intelligence, emotion, free will?
We are interested in emulating human vision in a computer. That is the capture of images, the processing of images, and then trying to figure out what's in the scene.
Many of the classical sciences are becoming information sciences or computing-intensive sciences. So computer science is in a renaissance.
One of the great challenges that we face in networking in the next few years is to take a fundamental look at how the internet works. The internet is now roughly 30 years old, and it is starting to show its age. And many of the problems that we have today couldn't really have been anticipated.
How do you balance the privacy issues with the need for knowing if something bad is happening on your network? Well, it turns out that a lot of ways to do it, but one of this involves strange and wondrous techniques from cryptographic theory. It's engineering, it's math, and it's also art.
We are essentially overwhelmed with information. A very difficult challenge is how to make all that information accessible in an easy way to the lay user.
There's this parallel evolution where the data is increasing in volume and the computer capacity is increasing. And it's hard to know, who's going to win.
The real hope is to use computers to help us make sense of the data automatically. We want them to learn much the way people learn and also work with the types of data that we care about.
A great many people are trying to find the magic bullet that will detect whether a person is lying or not. So one thing we're looking at here is how different personality types will produce deceptive speech versus truthful speech. And we're actually having some success with that.
And by making algorithms that are more efficient, that take less time, that take less space, we can make things that are literally impossible right now, completely possible in the future.
In terms of waves of the future, asynchronous is critical because it becomes basically close to impossible to design extremely large, complex chips, and we're heading to 1 billion transistors on a chip. So power is an important benefit of asynchronous because in a synchronous chip, you are constantly pumping your clock. Your batteries are winding down really rapidly. So you want to design chips that can harness this power and have a really long battery lifetime.
Lately, I've worked in something called autonomic computing, a software system that sort of automatically monitors itself and sort of repairs itself and fixes itself, sort of like how we automatically breathe and our heart automatically pumps and all this stuff without the brain having to do anything about it.
It would be wonderful if we could come up with a model of a human cell that would allow us through computer simulations to see how it would react to drugs, so we could perhaps find cures or causes for diseases.
I think computational biology is one of the futures of computer science. It combines both computational sciences as well as the healthcare research, which is going to be the major breakthrough of the century. One area that's pretty hot is medical robotics. We all know that in the future that's how surgery is going to be done. I'm also excited about our work with robotic and human hands. We think that by understanding human hands and trying to make robot hands work as human hands, we can really enhance what a robot can do.
There are laws in computing like there are in physics, that certain things you can do, certain things you cannot do, and I'd like to know what are the laws of computation. The biggest puzzle in computer science is a famous question called P equals NP. In rough terms means, is it as difficult to find something or to discover something as it is to recognize it when you see it?
So it really is a remarkable time in the history of computer science because one is able to look at an entire panoply of problems which one wouldn't even think about looking into because of its complexity maybe 20 years back.